Okay, let's have a warm up with some questions. I'll pop all these on now so you can pause the screen before I go through them. So I'll have a pause now. Good. Right, let's go through them. Number one, how can you test if two breeds of dog are the same species? There's a question on this that we did before. We need to make them breed and see if their offspring is fertile. Okay. It turns out that, yeah, dog breeds are all the same species, even though they look, vastly different. Some of them, like a Great Dane is massively bigger than a Chihuahua, but they're the same species because their gametes are still compatible. Number two, suggest how you could test if a specific phenotype, an observed characteristic, is 100% genetically controlled in humans. Yeah, so is freckling 100% genetic, or is it controlled by the environment a bit? Well, you could do a test by just doing identical twin studies. So you could look at identical twins. If one has freckles and the other doesn't have freckles, then you know that it's not a genetic characteristic. Yeah. So yeah, you can survey lots and lots of twins. So they do twin studies to do that kind of stuff. 3, how can new alleles of genes appear? That's just due to mutation. So mutation changes the DNA. That can just be a random copying error. Every time the DNA is copied, you can get new bases popped in, or it can be accelerated by exposure to ionizing high energy radiation like ultraviolet light, X-rays, etc. Some viruses can cause it as well. And there's something else. Oh yes, carcinogenic chemicals. And smoking is a risk factor for lots of cancers because the chemicals in the cigarette smoke, can physically react with the DNA. 4, what evidence do we have that all life on Earth is related to each other? Well, all life on Earth, you'd have to use the fact that it's a universal genetic code. Yeah, the codons, AUG codes for methionine, the amino acid, in all of life on Earth, apart from a few weird bacteria. But yeah, and that's just chance. The chance that everything has the same coding system is down to the fact that that tRNA with a it's AUG, it'll be UAC. A UAC anticodon always carries methionine. Is just down to chance. It's not as if the UAC causes that. It's just the fact that there's an enzyme that links them. So again, yeah, evidence that we're all related. Oh, it's coincidence. 5, what's an ecosystem? This is what you've hopefully done. Mrs. Huff sent did this for the year 13 stuff that you've started. Yeah, and it's all the populations in a habitat. I'm just defining community there. Sorry, I'll start again. An ecosystem is all the populations plus the habitat, or it's the community plus the habitat, or it's the abiotic plus the biotic. We're going to look today at how do we measure populations in a habitat. Okay, so that's the kind of link that I've just messed up a bit. So once we've defined a species, we can measure species in an ecosystem. If I know what it is, I can then start to measure them. Okay, and it's important that we know what's there, because then we can monitor what's changing. So here's a lovely habitat. This is a wildflower meadow that we don't really get in this country anymore. They've mainly gone because we use modern farming techniques. When we take in the hay, which they'll be doing so soon, I guess, because the grass is growing like mad now in this wet, dry warmth that we have currently. A tractor comes along and in a few hours it clears the entire field. Whereas in Romania, where this is, they still use scythes, so it's still like it's generally manpower with a scythe chopping down the hay by hand. So you can only clear a small amount of it at a time, and that means that you get massive diversity of flowering plants. Therefore, you get massive diversity of insects. Therefore, you get massive diversity of birds, and therefore you get big, long food chains, and therefore you get bears that can feed on, because it's such a massive massive food chain. There's a link here that I'll not show you via this, but I'll include it. This is just from when our school went on an Operation Wallacea trip to Romania to do all this counting. And there's a video of our school, kind of doing the ecology, doing the counting. And the aim was that we counted butterflies, small mammals, bears, birds. I've said butterflies, haven't I? What else do we measure? Anyway, lizards and things. So we kind of measured everything in different places, and they do that year on year on year, because Romania's joined the EU now. It's got richer now, and therefore they're losing these kind of old school farming techniques and bringing in more machinery, and therefore they're seeing the effect on the habitat. Yeah, there's not many wildflower meadows left. The EU tried to protect them all, but they then gave a date in the future, and therefore they all got kind of like ploughed up in the UK because they were going to be protected in a future date, and therefore that meant that a farmer couldn't do anything with them if they left them as a wildflower meadow. So a lot of them got destroyed in the UK. Yeah, awful. Anyway, I'll include that link in my kind of email that I send you, and you can watch it if you wish. There's no need to see if you can spot me. I'm on it, and Miss Friswell on it, and my partner's on it, Miss Doherty's on it, who kind of joined us. And yeah, they picked her to speak, and they picked another sixth former, both of which had like kind of like northern accents, which I thought was a bit not racism. What is it? Accentism. Anyway, who knows? I spend my life saying who knows, especially nowadays. Right. So what we're going to do. So hopefully you can download this sheet, and it doesn't really matter if you have the sheet or not. But we're going to use this sheet that's got this picture. So these are showing insects, like a photograph of the general insects in a habitat. And I've got 3 species here. Yeah, they're recognizable by their different morphologies, their different body shapes. Yeah, A is one species, B is another, and C is a third species, and there's lots of species C. So this is like a typical area. If I extrapolate it out into a bigger area, I'd still get the same proportions of A, B, and C. So A and B are rare, C is common. Okay, I did draw these myself using the draw tool in PowerPoint, so I was quite pleased with them. Calling them separate species takes knowledge and understanding. Yeah, because there's a thing called convergent evolution. Here's a dolphin and a shark. To someone who's not too sure, they might classify them both as fish. Yeah, we know that a dolphin's a mammal, and we know that the fish is the shark. However, if you're ignorant, then you might not know that they are different things. So yeah, it does take some kind of specialism to know it, and it's quite it's quite obvious when you look in detail. But for some things, it's not that obvious. There's two kind of like brown mice. They look identical, but they're different species, because one's lives in one place, one lives thousands of miles away, and there's a desert in between them, and they've just evolved to be brown mice because they live in a brown habitat, and therefore they've developed pigmented fur because that protects them from predation pressure from birds from above. That gives them better camouflage. Yeah, but they're separate species, but to the layman they just look like the same thing. But if you make them breed, they don't give birth to fertile offspring. Okay, yeah. So there is a thing called convergent evolution. I think in the Christian Bible it says that you shouldn't eat these birds, and it names a lot of birds, and then it mentions bats as well. So they just thought bats are birds because they fly in the sky and they have wings. So yeah, it's not always easy. You need experience to know what a species is. Hence we use like classification keys and things, which if we were doing proper field work now we'd be using, but we're not. Anyway, there's 2 ways of measuring this. There's species richness, which is easy. There's 3 species. There's A, B, and C. Okay, that's easy. You can just spot them. Okay, use your keys to know if they're a species, to identify them. What we're going to do today, though, is work out a diversity index, because I want to measure of this proportionality, that there's more of C than A and B. So I want to be able to measure that and kind of convert this entire picture into a picture. I can convert it into 3, the species richness, and I can convert it into a diversity index, another number, and that means I can monitor it over time. So that's what we're going to do today, is do some diversity index work, and there's a formula to use and a formula to understand. So you've got this sheet. At the top, just we did this on the previous one anyway, and that species richness is just the number of different species in a habitat, not how many there are, just how many different species there are. It's really quick to do. So I'm going to go through this diversity index problems, okay, and how to do it. Again, you can, if you're happy with one, feel free to stop. So our first one is based on this picture. Where's my picture gone? I seem to have lost my picture. Anyway, it's small here. I've got one of the yellow ones, I've got one of the red ones, and I've got loads of the black ones. And if I measure them, I get that, yeah, I've got one of A, one of B, and then there were 21 of the black ants. Okay, so those are my numbers of each species. So a small n is the total number of organisms of each species. So I've got one species of A, one of B, and 21 of C. If I add all these up, I get to a big N, 23. So the diversity index formula is big N, which is the total number of organisms of all species, how many insects there are on that page, times by the big N minus 1, okay, which we'll get to in a minute. So our big N is 23. There are 23 insects on that picture, okay? So that's big N's are easy. It's just how many things are there. Then the bottom of the equation is the sum of little n, which is the number of each species, times by little n minus 1. So we use the rest of this table to work that out. So 1 minus 1. So I've got my little n. I want now little n minus 1. So n minus 1 is 0, 0, and 20. And then n times n minus 1. So it's just this column times this column. That comes in at 0, 0, and 420. So the total of that is 420. So then I can just write that my diversity index D equals 23 times 22. So that's big N is 23. So this is big N at the bottom here. I'll put my laser pointer on. So yeah, 23. So that's big N. 23 minus 1 is 22. So that's where I get 23 times 22. So that's the top part of my equation, divided by 420. That's the sum of n times n minus 1. So that's 506 over 420, and therefore my diversity index is 1.2. It's utterly meaningless, is this? Okay, it just means that I can monitor it. If I come back next year and do the same thing again, and my diversity index is 1.8, that means things have changed. Okay, so it just means I've got a number, and if you have a number, you can plot it. If you can plot it, you can see trends over time. So that's all we are doing. So let's go through another example. So that's one. We're now I've increased the big yellow coloured one. Okay, I've kept that as 1. So there's still 3 species present, but there's more of a balance now. Okay. And I've kept the picture on this time. So again, feel free to pause it and work it out for yourself and see if it matches, but let's just go through it. So I count up A, got 5 of them, 5 of those yellow ones. B was the ladybird type one. I've got 1 of them, and I've got 17 of the ants. I've still got 23 insects in total. Okay, so my big N equals 23. So the top of my equation is 23 times 22. Then I do my little n's minus 1. So for species A, I've got 5. 5 minus 1 is 4. 1 minus 1 is 0. 17 is 16. 17 minus 1 is 16. Times those across. So I get 20, 0. Almost said 1 again there. Yeah, 0 times anything is 0. And then 272. Add that up, I get 292. Okay, so the bottom of my equation is 292. Because that's the sum of n times by n minus 1 for each of the species. So I get 23 times 22 divided by 292. That's 506 divided by 292, which is 1.7. So my diversity, I've still got three different species, but the balance has changed. It's become less dominant by one species, and that's reflected by my diversity index having a higher number. Okay. Really, you need both. You need your species richness and your diversity index. If you've got both of those values, it tells you everything. I don't need everything else. Okay. Let's have a look at another one. So now I've got even more balance now. So we'd expect the diversity index to increase further. Still got three species, but there's even more of a balance. And let's see if it works. So I've got 5, 6, and 12. Total of 23. So I'm keeping the same every time on the top. Do my minus ones, times them together. You get 182. So it's 23 times 22 on the top divided by 182, which comes in at 2.8. Okay, so yes, the diversity index has increased further. Let's have a look at one more. Well, no, I brought in some more. I've got two other species present now. I've got 5 different species. Okay, so let's see what we get. I've done this for speed. I've got 6 of every species now. So they're all 5. They're all 30. 6 times 5 is 30. So I get 30 times 29 divided by 150. I get a diversity index of 5.8. Okay, so the more different species there are, the bigger the diversity index, and the greater the more even the balance, the greater the diversity index. Okay. Again, we use the word diversity for humans as well, don't we? So, but yeah, in biology, it's a habitat that shows high diversity. There'll be lots of different species, and there won't be like one main dominant species. You know, farmers, if I'm growing corn in my field, I want a diversity index of 1. I want there to be, no diversity. I just want corn there. I don't want any insects eating it. I don't want any weeds growing. I just want 1. Okay, and you can show that if the habitat was all ants, so I've got 1 species present, well then it doesn't matter what this number is, n, because I'm going to divide n minus 1 by n minus 1. So I've got 21 ants, so I've got 21 in total. 21 minus is 20, 420. So I divide 420 by 420. I get a diversity index of equal to 1. So a diversity index of 1 means that there's only 1 species present. You can't get a lower number than 1 for a diversity index, unless you had like 0 here, and then you'd get 0 by 0. You get 0. But assuming there's something there to count, you're going to get a diversity index of 1. I can't get a diversity index of 0.4. It's impossible. So if there's anything to count, I get a diversity index of 1, and then the bigger the number, that just means that it becomes there's either more species or there's greater balance. Hence why we also use species richness. And we're going to use this later on and in the lesson next week as well. In terms of next week, again, some of you will be in. And therefore, because that kind of takes up teacher time, there'll be kind of like 3 lessons between your 2 teachers going out, because obviously you're going to have less time to do work because you're going to be in, or you're going to be catching up from the stuff that you've missed by not going in, and therefore, so there'll be 3 things sent out, 2 from one teacher and 1 from the other. Again, we'll finish the Year 12 syllabus next week, and therefore we're just kind of ploughing through the Year 13 stuff that's all about ecology, and then we're also going to be doing some like how science works and math skills type stuff, just to kind of get ahead. Again, we've saved time because we've not had mocks, and we've not been doing the actual going out field working, which saves like a week. So we've saved like half a week by being in lockdown, so we've got more time to kind of underline that kind of learning. It might be beneficial in the future, who knows. I'll just talk about this quickly, just because it's going to help introduce the next sheet as well. So I've got two habitats. I've got a jungle habitat, tropical forest, and I've got a desert. And habitat A has got a mean daily temperature of 25 degrees C, and B's got a mean daily temperature of 35 degrees C. So which is which? Which is the desert? Has that got a mean daily temperature of 25, or has it got a mean daily temperature of 35? Which is the hottest here? Yeah. So in a desert, it's blazing hot during the day, but there's no cloud cover, there's no trees, so it heats up during the day, and then it's freezing cold at night. So if it gets up to like 50 degrees C during the day, but it's 0 at night, it's going to have a mean daily temperature of 25 degrees C. Yeah. So yeah, it's actually the mean daily temperature, day being 24 hours in a desert, is yeah, is actually colder than a tropical forest where there's loads of cloud cover. Okay, and therefore it's hot all the time. The heat can't escape, it gets trapped, and therefore, it's hot during the day. It doesn't get much cooler at night. It drops by a couple of degrees or something. So yeah, this is going to have a warmer temperature. So in terms of where's the hostile place to live, this is the hostile place to live. Yeah, it takes a very specialist organism to be able to deal with massively fluctuating temperatures and arid or dry conditions. So it's hard to live here. So the diversity index here is really low. I'm seeing like there's a bit of maybe some grasses over here. Yeah. But yeah, it's really hard to live here. So hostile conditions equals very low species richness and very low species diversity, the diversity index. Go to somewhere where it's really favourable to plant growth. So again, it's in the tropics, so there's no seasonals effect really. There's a slight fluctuation, but there's hardly any difference between summer and winter if you're equatorial. The further north and south you get, the more pronounced the seasons become. That's why we're in a good country, because we get a nice change. Yeah, it's not blazing hot and freezing cold, like it is like in the north of Canada where you're kind of snowed in for 3 months. Here, we've got, it's a bit drizzly, it's a bit mild, it's nice. Yeah, it's always something to talk about. At least we've got the weather to talk about if we meet someone who we've never met before. It's rainy today. It is rainy today, but warm. Yeah, it's warm and rainy. Yeah. Anyway, much like it is in a tropical forest, and therefore that's plants love it, don't they? That's what we're trying to do in a greenhouse: make it warm and water the plants every day. So loads of plants can live here. Therefore, there's a massive diversity of plant species. So yeah, the species richness for plants is super high. The diversity index is super high, and because there's so many different types of plants, there's loads of niches, loads of different niches, places to live and things to feed on for animals, and therefore there's a massive diversity of animals there as well. Yeah, there's a cacophony of noise of screeching from birds and insects making little kind of, they make stridulation noises where they basically rub their like wing cases against like a comb organ, so it kind of makes a noise, which comes across like a noise. That won't come through well on the video. I'm going to stop there because the sheet that I'm going to get you to fill in next week is going to refer to hostile and favourable conditions. But I just thought, because it's on the end of this PowerPoint, I would show you. So I'm going to stop there. Hopefully that was enjoyable or tolerable.